Alright, in this video I'm going to teach you how to simplify a square root, or to write a square root as an exact answer instead of an approximate answer. So the best way to show you is just by working some examples. The square root of 8, one thing I could do is just take the square root of 8 and get a decimal answer, and I could round this to 2.8. That would be an approximate answer. But if I want to simplify this and keep it exact, then I need to take the factors, the prime factors of 8, to look at those. So you want to start off by making a factor tree for the number in the square root. 8 is divisible by, I could divide it lots of ways. I can divide by 2. Actually, no, 8 I can't. I can just divide it by 2 or 4. But 2 times 4 is 8. 2 is prime, so I'm going to circle it because that branch of the tree is finished. 4 can be broken down into a 2 times 2, and those are both prime. So I get 2 to the third. That would be the prime factorization of 8. But I want to pair up my factors because I'm dealing with the square root. So I want to write it a little differently. I'm going to look for all the pairs of factors I have. I have one pair of 2's, so I'm going to write it as a pair, 2 squared. And then this 2 is left over unpaired, so I'm just going to multiply by 2. This equals 8, so these two are the same thing. They're equivalent. Now what I can do, I'm going to do a little side thing here. If I have the square root of 2 squared, the square root cancels the square because they're inverse operations, basically. So what happens is the 2 comes out and the square root and the square are gone. They've canceled each other out, and you get the number back that you started with. So here, for every pair that you have under the square root, one of the numbers comes out. So 2 squared, I can bring out 1, 2, even though there's 2 of them multiplied under the root. 1, 2 comes out, the 2 squared is gone, and I'm going to put that right in front of the square root. So this equals 2 in the front. This 2 is left over, nothing happens, he has to stay inside the house, and so he's left under the root. And the exact simplified answer would be 2 times the square root of 2. That one's pretty simple. Let's do a bigger one. Second example, let me make sure I'm still in view. Let me slide this up. All right, let's do the square root of 48. So I don't want to get a decimal for this. I could do that on the calculator, but that would be an approximation. So I'm going to take the 48 and break it down with the factor tree. You can divide. There's lots of different ways I could divide this. Your tree might have a different shape, but in the end you should end up with the same set of prime factors. I could say, I could do this, 4 times 12. That's one way to break it down, or let me do a separate tree. I could go 2 times 24 to start with, doesn't matter. So in this case, 4 times 12, neither one of these is prime because they both can be divided further. 4 can be divided by 2, and I get 2. 2 is prime, so that's the end for those branches. 12 I could divide by a 3 and a 4. I could have also done 2 and a 6. 3 is prime, but 4 can be further broken down into 2 times 2. So I have 4 2's and 1 3. Now, if you want to see how this one looks, the 2 is prime here. 24, I can divide that by 2 and I get 12. 2's prime. I can keep dividing by 2 and I get 6. and I can divide that by 2, and I get 3. So in either case, I have 4 2's and 1 3 for the prime factorization. Now, I'm going to pair those up, pair all the prime factors up. And one thing to note, you don't, for example, if I take this 2 here, I don't want to divide by 2 if I'm going to get 1, because that means if you get back the number, the only factors are the number in it and 1, that means that's prime. So you don't want to have any times 1s in your tree at all. But I do have 1 pair of 2's, 2 pair of 2's. So 2 squared times 2 squared. And then I have a 3 left over times 3. 1 2 comes out for each of these pairs. So 1 2 comes out for that one. 1 2 comes out for that one, and those are both gone, so cross them off. And then each of these 2's is going to go in front of the square root. So I get a 2 times a 2 in the front, 3 is left inside. And then if anything can be multiplied, if you have numbers left over inside, more than one number or more than one number on the outside, multiply them together. So this is 4 times the square root of 3. And that would be the simplified version of the square root of 48. Now let me do, I think I'll do one more. No, maybe 2. Example 3. I'm getting bigger each time here. Let's go with the square root of 360. So 360, I'm going to divide by 10. 10 times 36. And 10 isn't prime because I can still divide that by 2, and I get 5. Both of those are prime numbers. The only thing I can divide them by are themselves, or 1, and so you don't want to do that. 36 I can divide by 3, and I get 12. Circle the 3, it's prime. 12 can be divided by 3 again. I get 4, and then, oops, sorry, I should not have circled the 4. The 4 can be divided by 2. 2 times 2. So I have 3 2's, 2 3's, and 1 5. Now I'm going to take the pairs in those factors. So let's take, here, let me highlight these. These 2 3's go together, and I have 2 2's that go together. These 2 don't pair up with anything, so they'll be by themselves. So 2 squared times 3 squared, and then times 2 times 5. Now, in this pair of 2's, so 1 2 comes out, cross off the 2 squared. 1 3 comes out, cross off the 3 squared, and the 2 times 5 is left under the square root. So I get 2 times 3 on the outside, and left inside is 2 times 5. Now you need to multiply those numbers. So the final answer is 6 times the square root of 10. So hopefully it's making a little bit more sense. Let me do one more. So I'm going to flip over to the back side and make sure I'm on my paper. Yeah. Let's see, that was, let's do number 4. Example 4. All right, let's go big this time. The square root of 3,780. So I'm going to have kind of a big tree here. 3,780. Let's divide by 10, just because I can do that quickly. And I get 378. Your divisibility rules can help here too. If I add up all the digits, I get 15, 16, 17, 18. They add up to 18, which means I can divide this by 3. So divided by 3, it's going to be 378. Gives me 126. The 3's prime. Adding 1, 2, and 6 together, I get 9. I could actually just divide by 9 if I want, or I could divide by 3 again. So I'll divide by 9. And 126 divided by 9 is 14. Neither of those is prime. 9 goes down to a 3 times 3. 14 is divisible by 2, and I get 7, and both of those are prime. So my tree is finished this way. The 10 is not finished, so I can divide that by 2, and then 2 times 5. So pairwise, I have 2 3s and 2 2s and a 5, 3, and a 7. So I'm going to have 2 squared for my pair of 2s times 3 squared for my pair of 3s, and then times 5 times 7 for my leftovers. 1 2 comes out from 2 squared, cross it off. 1 3 comes out from 3 squared, cross it off. And those are going to go on the outside of the square root, and I'm going to multiply them together. So 2 times 3 means 6 on the outside. And then left on the inside is 5 times 7, which is 35. So the square root of 3,780 is 6 square root 35.